Hello, so let's begin with this class. So one of the big topics of today is going to be about convolution. Okay, so that's really the end of this chapter on Lebesgue integral, and I promise you it was maybe one of the most theoretical chapters of the year. Okay, so don't worry, it's going to be a bit more practical very soon. And even with this topic of convolution, I will propose you one activity that is doing some numerical application of this. And the application that we are going to do are about working on some images and finding how we can do some simple edge detections of the shapes in the image, and some blurring and simple things like this, which can be done with what is called convolution. Okay, so convolution is a tool, a mathematical tool. It's a mathematical operation that appears in many applications actually. So, and that appears to be quite fundamental in the end. So let's read the first that first paragraph, which again is, I'm sorry about that, but it's really very, I think, one of the clearest definition or approach of convolution that I've seen from Wikipedia. So the convolution, first of all, it's going to be a mathematical operation. So in order to perform that, we need two functions. So they're going to be called f and g. And we have this notation with this nice little star here. Okay, so that's the convolution notation. And we make a third function. So that's going to be f convolved with g. And so let's say that it's going to be a function that depends on x. Okay, and it expresses how the shape of one is modified by the other. Okay, this seems a bit vague for the moment, and we will see on some specific examples how it can get a bit more sense. But well, let's refine that a bit. The convolution formula can be described as a weighted average of the function f at some moment where the weighting is given by the other function simply shifted by the amount of t that we are looking at. So in the formula that I've written, I've used x and y. So what would be the equivalent of t? That would be my x, and the tau would be given by the y. Okay, so what is that? It's really defined by an integral, so that should remind you of a lot of good memories from the past weeks. Okay, so this function is defined by an integral, and it's really a parameter dependent integral. So the parameter being the x here. Okay, sorry, that's the parameter that which defines the argument of the function we're computing, and the variable of integration is the y that we have here in both functions. So we've got g of y, okay, and we've got f of x minus y. That's the f that is shifted by the amount. So that's the shift, okay, that the operation that is indicated here, that represents a shift. Okay, so maybe before we go on on some simple examples, so that's just a formula that you have to know, and to know how to apply and to know how to calculate, and that's what we're going to do today. And in the tutorial, we will learn how to calculate this. Okay, and again, it has a lot of different applications. One of the very clear applications we're going to see is what's called the Fourier transform that we're going to do in a few lessons. Next lesson is Fourier series, and then we will go for Fourier transforms, which are very nicely related. Okay, so before we do some actual computation, let's have a look at the Wikipedia page again, because you've got some nice visual explanations. So can you have a look at this? So we've got two functions. Let's look at the animation here. You've got the on that first graph here, animation, you've got that blue signal, which would be it's the f here, but in the formula I've given, it really looks like the g. You have another one, the red one, and So as the red one moves along the real line, at some point it crosses the blue one, and so that's, and you get an area, that's the yellow area. That's defined as the area under the product of the two functions. So here you've got 1 times 1, so it's very easy. It's just areas of rectangles. And then you compute this area at every value of t. So that's really a shifting average. That's maybe the keyword that you want to remember. Shifting average. And the value of this shifting average, so it's an average at every value of every real value, so that produces that triangle that you see appearing here. That black triangle, that's the result of the convolution. Okay, so that's the new function that is created. So here you've got an example with two rectangle functions. So the red one and the blue one on the first animation. Second animation, you've got some other kind of functions. So you've got a red one, which is still a rectangle function, and another one, the blue one, which well, that's some kind of a pulse. And so in that case, you see the convolution, the black curve that you see that is drawn here during the shift on one on the other is looking like the first one that has been that has been smoothed by the second one, something like this. Okay, that's more or less the idea. Okay, so let's compute some simple example first. Okay, so let's do one example. I have rewritten here the formula of the convolution. All right, so let's go and write it. What's happening for the convolution. Let's take some function f, any function f. All right, I'm not saying anything about its regularity or the fact that it may or may not belong to any of the LP spaces. We will see that later on. Okay, but let's say that I'm taking some functions so that the formula is going to work. All right, so let's choose a function from R to R, and it may be in C, but let's take R to begin with. And we will define so one function that we're going to use quite often called the gate function, or the rectangular function, or the box function. Okay, and it's just going to be the one that is 1 on the interval AB, okay, which could be open or closed, but let's write it this way, AB. So 1 over x, so the indicator of that interval, and let's divide by the size of this interval. Okay, so that in the end, if you compute, so what does it look like? Of course, sorry about that. It just looks like as something, let's say that this is A and this is B, and your function is 0 before A, 0 after B, and before that, the value of the function is 1 over B minus A. Okay, so that if you do the area below that curve, it's equal to 1. Okay, that's area of 1. The integral of this function is equal to 1. Okay, and again, the name is gate function that acts like a gate in signal processing or other physics topics. Or the rectangular function. I think if you want to address this function on Wolfram Alpha and maybe in Octave, you have to use rect as an indication of the function, or box function. Okay. All right, so that's this function. Let's compute the convolution of those two things, right? F convolved, so that's a nice little star. Well, that should be a nice little star with this pi of AB function. All right, so that creates a new function that, let's say that it's going to be on pi. Okay, so what does it look like? It's first, so let's write the complete stuff. The integral on R of f x minus t. G now is my gate function, so I have 1 over b minus a, indicator of interval ab of t dt. Okay, so let's work on that. first, you know that, well, I can first maybe put my constant outside of this integral. Then I can reduce the bounds of my integral to ab because of this indicator function. And what do I have left? F of x minus t dt. Okay, so let's get a bit further using this. Let's use some substitution, right? Because I would like to relate what I have obtained here, this thing here, to, well, something more like the integral of f. It should be a bit clearer. All right, so let's use some substitution. So substitution. Let's put a new variable. Yeah, let's use u is equal to x minus t, so that I will be able to write f of u in my integral. So I've got that du is minus dt. And we have that if I plug that substitution, I still have 1 over b minus a integral. So when t is equal to a, u is equal to x minus a, and when x is equal, when t is equal to b, u is equal to x minus b. Okay, and then I've got f of t dt. Oh, sorry, there was a minus trailing here. F of t dt, the minus coming from the minus du, but that's good because if you see that the interval that I want to integrate on actually is going to be x minus b, x minus a, because if b is greater than a, x minus b, we assume that b was greater than a when we wrote the function first. So x minus b is smaller than x minus a. Okay, so now I can bounce back my bounds of integration, and that's just going to be the integral between, so 1 over b minus a, integral between x minus b, x minus a of f of t dt, and we now can have a clear interpretation of that. I'm integrating my function on an interval of size b minus a, and I'm dividing by b minus a. That's exactly the mean value of f on that interval. Okay, so the convolution of f so that's an interval of size b minus a that is centered in x. Okay, so the value of the convolution of the two functions, f convolved with my pi function in x, at each point x, it gives you the value of the, well, it's given by the mean value of the function f on an interval of size b minus a centered around x. Okay? Right, so this is why we call that, the interpretation that we can give of this calculation is like a moving average. Okay, we take the mean value, the average of the function f, but we just move the interval where we take this average at each point, so that it's just going to represent the center. The center of that interval is going to be the argument of your new function. Okay, good.